Let us to move to the last talk of the morning. And in this case, I would like to address some previous comments, because maybe it could be interesting for many people in the room. Along this school, we have people with a very important number of years among the back that have accumulated a lot of experience, a lot of knowledge, and many things. But the major number of people in the room are young people, are in the range of 20 and 30 years. And many people are doing the PhD. So in few years, or in few times, you are going to be doctors. The sample that we are going to see now is very clear example of how it's possible that one young person, okay, was working hard by weighing the enough mass of brain, can reach very important position worldwide. So the speaker that you are going to hear in a few seconds, you can find in the best meetings worldwide, speaking in plenary sessions, invited talks, everything, okay? So you, many of you, can do this job. This is the first comment that I would like to say. So it's possible to do by being young. But of course, not all reach these positions, okay? But it's possible. This is the first comment. The second comment is that the speaker did a PhD in Cambridge University just in 2012. So it's yesterday. And he moved to Sydney, changed the place in order to get new experience. And he now is working in Queensland University in Australia. So he came just from a very long place of the world from here. And the talk that we are going to hear, I remember when I was studying for the first time these topics, that we always thought that multimode was not so good system of communication because many things that happens. So we try to always monomode systems. But as everything in the world, in the life, sometimes everything is crowded. And we need to look for new technologies. And now, multimode can be used in order to do multi-channel communications in the same fiber. So the great merit of Joel Carpenter, Dr. Joel Carpenter, Professor Joel Carpenter, is that he did a very nice work concerning the multimode, the manipulation of the multimode light in order to do communications and many other things for a very wide set of possible applications, medical communications, images, and many, many other things. So welcome to Santander. Thanks to do so very long journey, okay? And I hope that your luck is now under control.
We'll see.
And it's your turn.
Thank you very much. Thanks for a very kind introduction. Yeah, I am relatively young, but I have the receding hairline of a much older man. It gets me part of the way there. All right, so, like I just said, I'm Joel from the University of Queensland, and most of my work is centered on measuring or manipulating the spatial and temporal properties of light, often in multimode optical fiber. It comes up in a lot of different places. Because obviously if you want to use the spatial or temporal properties of light to do something, the first thing you've got to be able to do is actually measure it or control it in some way, right? So I'm going to go through at the start and just mention a few different applications, a few different experiments that I've done over the years on spatial mode manipulation, but then I'm just going to settle on one, which I'll talk through most of the talk today. All right, so spatial mode manipulation. One place you might use it, which Peter mentioned briefly yesterday, is mode division multiplexing. So in mode division multiplexing, you've got n modes modulated with their independent channels of information. You assign each one its own orthogonal spatial mode, and then you put them both in the same fiber, or you can also do it through free space, and then through the fiber they get scrambled up, and then you unscramble them typically with DSP, and then you recover your channels like so. Another one is something called multimode fiber imaging. Now, multimode fiber imaging might seem like it's a quite different application than space division multiplexing, but they're actually quite similar based on this same idea that you have to put light in, it gets scrambled, and you unscramble it. So if you've got a multimode fiber, normally when you put an image into it, it doesn't show up as that image at the other side, it gets scrambled. Right? So if we put in our little focus spot like so, and then we look at it on the camera, you can see it just looks like this kind of random looking speckle pattern. Right? The image is not preserved. But it's not a random process, it's entirely deterministic. So there's a one-to-one relationship between the speckle on this end and the image on that end. So if you know the transfer matrix of your fiber, then you can invert it and you can effectively see straight through your fiber, right? You've got that map spatially between the two ends. So that means you can do things like this. So instead of having image in, speckle out, you can put this kind of pre-scrambled speckle pattern in at one end, and then it will focus or create some other image at the far end. Okay, so the idea here is that you could use the multimode fiber as a very thin endoscope. Okay, so you've effectively got all the pixels of your endoscope right on top of each other, because they're the modes of the fiber. So it's very high spatial density of information. You can also print things more complicated than spots. Obviously, here we've got one where I'm printing characters to the far end of the multimode fiber. Now, when light gets scattered spatially in a medium, it also tends to get scattered temporally as well. So you can also measure that and compensate for it. Let's say we've got some arbitrary spatial state, like so, and it's got some arbitrary temporal properties as well. So each one of these speckle grains could have a completely independent impulse response. And then we can put that into our scattering media. Could be a multimode fiber, could be biological tissue, could be a lot of things. But if you can measure that linear process from input to output, the optical transfer function, then you can predict what that new spatio-temporal state will be that pops out the other end. So there you would use that for something like mode division multiplexing, you need to do that. But also just whenever you're trying to deliver light in a certain way through a scattering media of some kind. Right? If you can characterize the properties of the media, then you can compensate for it and focus through it, etc. One example of why you might want to measure the spatio-temporal properties of a media is characterization of novel waveguides. If you've got this one here, we've got a photonic bandgap fiber, launch something in at the input, and then just measure the properties of the light that come out on the other side. And you can get a lot of information out of it. So here's a spectrogram. It's got all the spatial information, polarization information, time information, wavelength information, basically the works. Okay, so we launch something in, we get this spectrogram out at the output, and then we can see for every wavelength, at every delay, we get an image of what the modes that arrive at that time look like spatially, and then also they've got little polarization vectors jittering about there as well. Well, it's obviously very useful for characterization, useful for compensating for scattering effects. The other thing you can do is, because previously it hasn't been possible to measure these spatio-temporal dynamics in such detail, so once you've got that data, you can just start rifling around inside it trying to find novel spatio-temporal phenomena that people haven't previously observed. And one of those is a thing called Wigner-Smith states. They're also called principal modes. They were proposed a long time ago in the scheme of things, but no one had ever actually seen them before, mostly because no one would be able to measure the spatio-temporal scattering. So what are they? Normally, you would put in light, say into a scattering media like multimode fiber, goes in looking nice, pulse looks nice, propagates through, then it gets scattered. And it comes out the other end, completely distorted in time, and also spatially it's scattered all over the place as well. That's a normal sort of scattering process. And if you looked at it in the wavelength domain, every wavelength would be completely decorrelated from the other ones because of this temporal behavior here. Okay? So it's normal scattering propagation. But there are special states where you can send them through the scattering media, and they'll show up at the other end without any temporal scattering in the time domain. So you put them in, and then somehow they show up at the other end, maintaining that single pulse. They arrive as a single delay. Those are called principal modes or Wigner-Smith states. That also means that they're wavelength independent. So if you tune the wavelength of your laser, the output stays rock solid, which is kind of weird. It would normally do that. You can have a state that manages to somehow sneak through without undergoing any scattering, or you can also have one where it just tends to cancel out at the other end. Both are possible. So probably just ignore that graph here, but what we're looking at the moment is an example of one of these states. Let's say you do a normal launch into a multimode fiber, and then you change the wavelength of your source. The output speckle pattern would change and go all over the place. Okay? That's what you would normally see in a multimode fiber. But if you launch in one of these special states, you can see that as we change the wavelength, it doesn't move, which is pretty weird. Right? That's what a principal mode does. Okay, so that was very quick little examples of just some spatial mode manipulation experiments. All of those could be a talk unto itself, and they are a talk unto themselves. You can check them out all on my YouTube page if you're interested in any one of those specific topics. But today, I thought I'd present something which I haven't actually presented before and isn't on the YouTube page, is this work on a Laguerre-Gaussian spatial mode sorter, which I'll explain in a second. Collaboration between myself and the guys at Nokia Bell Labs, particularly Nick Fontaine. So what is our Laguerre-Gaussian spatial mode sorter? It's a device that does an operation like this. You put the light in, goes through a cascade of phase plates, and then it decomposes the beam into a grid of points, and then each one of these points consists of a Laguerre-Gaussian or Hermite-Gaussian component that was in the original beam. Okay, so it's like a mode sorter or a mode demultiplexer. Okay, so it takes a beam up and it takes a beam and it splits it up spatially. Okay, so if you have something like a lens, you know that would do the Fourier decomposition of your beam. This does the Laguerre-Gaussian decomposition of your beam. And despite the fact that Laguerre-Gaussian is a pretty standard sort of basis in beam optics, there hasn't previously been a device that can do this, right? And why not? Okay, so we'll go through some reasons why not. Now, if we look at the wavelength domain, we look at spectrum, and we have a beam, and we want to split it up into its spectral components, that's pretty easy, right? People have been doing that for hundreds of years. Many different components you can use to do an operation like that, which maps beam in to wavelength out. You use a dispersive prism. You can also use something like a grating. Beam comes in, hits the grating, does a very similar operation where it maps wavelength to position on the x-axis. And then along here, we can measure or manipulate each one of those spectral components however we please. Okay? It's a kind of operation that you take for granted in the lab that you can just get a beam and split it up into its spectral components, and it's not going to be a big deal. Okay? Same with polarization. Again, splitting a beam up into its polarization, very easy. Many ways you can do it. They've been around for hundreds of years. Here's a PBS. Beam comes in. Two orthogonal polarizations come out the other two ports. Or just a chunk of calcite will do that for you as well. Beam comes in. Two different refractive indices for the fast and slow axis. Snell's law introduces an angle, splits them apart. Again, not a big deal. But let's say you've got a beam like this that consists of many different orthogonal spatial components, like the modes of a fiber, let's say, and you want to split them up in that basis. It's even harder to get the slide work. That's how hard it is. How do you do that? Okay? See? There you go. It is difficult. It's a particularly difficult operation. I don't know what that means, but I'm going to say this one. No, it's the wrong one. I had a 1 in 2 chance. All right, any questions? All right, hold on. Probably one of the least complicated slides in the whole thing. All right, let's see. All right, so hopefully that isn't a recurring theme of this. Okay, so are we going to split these apart? Yes. Okay, point was, wavelength polarization are tricky. Wait, they're easy. Space is hard. And one of the reasons why is that there's no like just piece of glass or crystal you can dig out of the ground that will just do this for you, right? That's not a thing. Whereas with calcite, dig it out of the ground. Glass, you just make it. It does wavelength splitting or polarization splitting for you. Nature was not kind enough to gift us with this operation. So you've got to build it yourself, which is what we do. So here we redo this slide. Through cascade of phase plates, you can decompose a beam from its Laguerre-Gaussian components to its to an XY grid. All right, so what do I mean when I talk about spatial components or orthogonal spatial components? The type of orthogonal spatial components that most people would be familiar with, especially if they're in the general public, is the idea of a pixel. Okay? We've got an arbitrary two-dimensional function, which will be our smiley face throughout the talk. And we can approximate our smiley face as a summation of a bunch of pixels with different weights. Okay? And all these pixels are orthogonal. They don't overlap with each other. You can't use one pixel to describe any other pixel. They're all completely independent. And if we want to make a better approximation of our smiley face, we just make a summation of more pixels that are smaller and finer. Okay? And that's fine. But little square pixels, flat pixels of light are not really a thing in optics. There's nothing particularly special about the propagation characteristics of a little square. It's just a convenient way of making things like CCD cameras, monitors, storing stuff in memory, that kind of stuff. Right? If we have our little square pixel of light and we let it propagate forward and diffract, it'll interfere with itself and it's not like it's going to stay like that forever. It's just going to turn to some other shape, which in this case is a 2D sync function. So with this color scheme, if you haven't seen it before, dark to white means amplitude, and then the color represents the phase. All right, so pixels, good for making devices, not really have any underlying physical significance to them. Another way which you could represent your 2D function is in the Fourier representation. In the Fourier representation, you'd be familiar with if you've done signal processing or imaging processing. You can get like a time signal and approximate it as a summation of its frequency components. So the same thing holds in 2D. You can get 2D function and represent it as a summation of its spatial frequency components. All right, so we have our smiley face. What that means for optics is you can approximate the smiley face as a summation of a bunch of different plane waves all coming in at different angles with different weights. All right? So there's our plane wave. It's infinitely large. It's flat. It's uniform. It doesn't have any property other than the fact that it travels in some particular direction, theta x, theta y, or kx, ky. And just like we did for our pixels, we can approximate our smiley face as a summation of plane waves tilted in different directions with different amplitudes and phases. Okay? And the more plane waves we add, the better approximation of our smiley face gets. The happier our smiley face gets, let's say, until it reaches nirvana at the end when we have an infinite amount. So the thing with the Fourier representation is it does have some underlying physical significance. So it does kind of actually mean something in physics, which is one of the reasons why people use it. One of the reasons is that if you let a beam propagate forward, it will naturally decompose itself into its Fourier representation. So free space propagation does the Fourier transform. So we look at our smiley face here, propagate forward, it diffracts, it turns into this new distribution in some plane far away. And this new distribution that we're looking at here is the Fourier transform of our smiley face. Each position here corresponds with the amplitude and the phase of a tilted plane wave that made up the original smiley face. That's it. The other thing which does the Fourier transform is a lens. Right? So the lens gets infinity, brings it to the focal plane, and it also does the Fourier transform. It also turns positions to tilted plane waves on the other side. So the Fourier representation has some more physical meaning than, say, pixels, because of the way that light propagates through free space and also through lenses. Like, obviously, there's a whole field of Fourier optics just devoted to this kind of stuff. The only downside of a plane wave-based representation is the fact that plane waves don't actually exist in reality. You know, they would be infinitely large, they'd have an infinite amount of energy. But even if you manage to somehow get your hands on a plane wave from somewhere, presumably Alibaba or something, you'd actually have to put it through a real optical system that has a finite size, so it's going to get clipped anyway. So you got your plane wave. Let's say it goes through a lens. Now it's not a plane wave anymore. Now it's a little circular disk of light. And we're effectively in the same scenario we were with the pixel. That also won't maintain its shape. It'll diffract and it'll turn into an airy disk in this case. Okay, so plane waves, good mathematical representation of how light exists, but they're not always a practical basis that you want to use because of the fact that they don't actually exist. Right? But there are special types of beams that have a finite size that do preserve their shape as they travel. Right? These are functions that are the eigenfunctions of the Fourier transform. They're also the solutions to the Praxial wave equation. So, you know, just like if you get a Gaussian, you Fourier transform it, you get another scaled Gaussian back. Fourier transform a Laguerre-Gaussian, you get another Laguerre-Gaussian back. And that means if we start off with our Laguerre-Gaussian function here, it consists of a bunch of rings with helical phase on it, and we let it propagate forward, it gets bigger, and the wavefront gets curved, but it still maintains the same shape. Right? So everything that's got a finite size is going to diffract out and get bigger and get a curved wavefront on it. But this thing maintains its shape. It still consists of helical wavefronts, number of rings. The basic shape is preserved through propagation. There we go. Hermite-Gaussian, same idea. Propagates forward, maintains its shape. Gets curved, gets bigger, but it's still got the same number of lobes, same dimensions, all that kind of stuff. Now, because of these special properties that Laguerre-Gaussian and Hermite-Gaussian modes have, in beam optics, fiber optics, Fourier optics, they kind of come up a lot in different areas. Okay, so if you're trying to transmit information, let's say, in some sort of mode division multiplexing scheme through free space, it's a good beam choice because it's preserved through free space. So if we transmit from here to here, then it's the same type of beam, that transmit and receiver. So it makes sense to use that kind of beam. The other one is, like I said, it's eigenfunction of the Fourier transform, which means it looks the same on both sides of your lenses. Right? Unlike our smiley face, which would look different on both sides, this one looks the same here, 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 everywhere. To some extent, there are also eigenmodes of parabolic index fibers in the weak guidance approximation, which means that, sort of, you put them in at one end of the fiber, a Laguerre-Gaussian mode, and it will pop out the other end as the same Laguerre-Gaussian mode. Right? In practice, it doesn't actually work like that. But because of the way that the Laguerre-Gaussian modes are so closely related to the underlying physics of how light propagates in multimode optical fibers, they're still basically the basis of choice for graded index fibers as well. All right, so with our pixels, we could get a bunch of pixels, add different weights, make our smiley face. Same with our angle basis, our Fourier basis. We could add together any one of these with different weights to approximate our smiley face. We've got two indices, tilt x, tilt y. Same thing holds for the Hermite-Gaussian basis. It's a 2D set, so we've got two indices, m and n. And we can approximate any function we want by adding together different weights of these things. Same with Laguerre-Gaussian. It's also got two indices, L and rho. So L tells you how many 2 pi worth of phase there is around the ring, and then rho, or r, tells you how many rings there are. Yep, and there we go. So approximating our smiley face as a summation of a bunch of Hermite-Gaussian modes. And just like for pixels or for plane waves, the more modes you add, the better approximation gets. Or with Laguerre-Gaussian. Laguerre-Gaussian slides are more fun to watch. All right, you get the idea. There's a lot of modes. OK, but if we've got a beam, and we want to decompose it in the pixel basis, that's pretty straightforward. You can just slap a camera in front of it, and you'll get a bunch of pixels out. You want to decompose it into its angle basis, you can use a lens. But if you want to decompose a beam into its Laguerre-Gaussian basis, you're out of luck. There hasn't previously been a device that can do that type of transformation. Right? So despite the fact that Laguerre-Gaussian basis is a pretty fundamental basis in beam optics, it's not like Fourier representation where you can slap a lens in front of it and get that decomposition out. There's not really been previously a way to decompose a beam into the Hermite or Laguerre-Gaussian basis. And that's where this device comes in. So I'll talk about this more in detail. How it works is we've got phase masks here, mirror here. Beam comes in, Laguerre-Gaussian components of the multimoded beam, bounce, 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 and then pops out the other side as a grid of points, and then each one of the points here corresponds with a particular Laguerre-Gaussian or Hermite-Gaussian component on the other side. Now, why is that so difficult? So why has that not previously been a thing that existed? Like we saw with doing wavelength to space mapping, very easy. Many things can do that. Polarization to space mapping, also very easy. Space to space is hard, though. And you can see one of the reasons why is that we've got this beam coming in, and we want to split it apart based on its spatial properties. But the spatial properties keep changing through the transition. They have to change. So the beam looks different here than it does here. We want to split it up based on spatially what the beams are, what the components are, but the beam keeps changing. Okay? So it's like you're trying to hit a moving target. So in general, you're going to need some sort of continuous three-dimensional refractive index profile that sort of adapts as it goes. Now, one device that can kind of do something like this is something called a photonic lantern. So a photonic lantern was originally invented by astronomers for taking multimode light off their telescopes, splitting it up into single-mode light for their spectrometers and filters and that kind of stuff. And it's a continuous three-dimensional refractive index profile. It's a tapered fiber device. It's got an N-mode fiber on one end that tapers out to N single-mode fibers on the other end. And if you put light into the multimode end, it travels through the transition, and it gets spat out as a bunch of Gaussian spots at the other end. Okay? And then it swims off for some reason. I don't have to include that slide, but I always include that slide. All right. Yeah, so the only downside with a photonic lantern is that it's not really very good at doing a precise mapping between mode in and particular fiber out. In general, it just scatters light all over the place. So you put like an LG mode into the multimode end. In general, it will just come out all over the place in all the ports on the other side. Okay, so it's not really easy to control a photonic lantern to say, I want fiber 1 to be Hermite Gaussian 3.2. That's very difficult. Not really feasible. An alternative is to use something called a multiplane light conversion system, which is a little bit like a discrete version of a photonic lantern. So a multiplane light conversion system can do arbitrary spatial basis transformations and arbitrary spatial basis decompositions. It consists of a cascade of phase plates, which I'll show in a second. We've got our input basis. Let's just say it's a line of spots. And then we propagate through phase plates, followed by free space propagation. And then we can morph from one basis to another, spots to modes in this case. So one spot on that side corresponds with one particular mode on the other side. So it's like a photonic lantern in that it's a three-dimensional refractive index profile, but it's lumped into discrete planes. And the advantage of multiplane light conversion is that you don't have to worry about trying to make this thing as a tapered fiber device. It's much more flexible in terms of the kinds of transformations that you can do. It's just a bunch of phase plates, and you can put basically whatever you want on the phase plates. It's much better for arbitrary spatial basis transformations. Key question is, though, how many planes do you need? Well, it depends. It depends on what type of spatial basis transformation you're trying to do, because some spatial basis transformations are much easier than others. But in the worst case, if you're trying to decompose a set of n modes, or transform n modes into n other modes, you could need as many as 2n phase plates, which could be bad. And if you want to make it work over a broad bandwidth, then you'll have to use even more wavelengths, make the transition even smoother and more adiabatic. And then you can imagine if you added an infinite number of phase plates that are all very closely spaced together, you've effectively got a completely continuous three-dimensional refractive index profile, which is like your photonic lantern. But like I said, in practice, these are all, or in theory, all these phase plates are lossless, so who cares how many there are? But obviously, in practice, you care how many there are, okay? Because the more there are, the more difficult it's going to be to make. And also, even the loss is going to scale with the number of planes as well. So even if each one of these has 0.1 dB of loss, and you've got 50 modes, so you need 100 plates, suddenly you've got 10 dB of loss for your so-called lossless device. Okay, so you want to try to minimize the number of plates that you have to use for complexity, and then also just for loss and other problems. But importantly, we already saw that some types of basis transformation don't require this full 2n number of phase planes. Some get by with way, way less. And the Fourier decomposition was an example of one. Either free space will do it for free, 0 phase planes, or a lens, 1 phase plane, will do that kind of basis transformation for you. Another one which is kind of trivial, let's say we want to change from a spatial basis of a grid of spots to a line of spots. That also only requires 2 phase planes. It doesn't matter how many spots there are, it's always just 2. You just need 1 phase plane to direct the spots in the direction of their new location, and then 1 to stop them once they get there. Okay? It doesn't matter how many spots, it's always just 2. Another one, which is relevant to us here, is something called an Azimuthal mode sorter, which actually seems to be very similar to what Professor Pendry was just talking about. It's a device which so the device we've got here, it can discriminate between both the radial index and the azimuthal index. So it can tell the difference between all of these different modes. Previously, people have invented devices that can just do this bit. So they can't tell you how many rings there are, but they can tell you how many worth of 2 pi phase there is around the ring. And that device works by a log polar transformation, which basically puts a slice in your ring, unfolds the ring into a line so that that helical phase is now a linear phase. And then once you've got the linear phase, you put it through a lens, and linear phase becomes offset. So you map phase around the ring to a specific offset on the other side. So we've got our helical mode here. You put that log polar transformation mask on it. You let it propagate. Oh, that propagated too much. All right, well, there's some propagation in between these 2 planes, but then you end up with a line, okay? And then when you focus that line through a lens, that's also got a lens on it. I think it's struggling a bit. Okay, so the point there was that you get the ring, you unwrap it, and then it maps it to a position on the other side. But the important point is that it doesn't matter how many modes you're trying to sort. It's always just 2 planes. Okay. Same thing with Hermite Gaussian to Laguerre Gaussian transformation. That's also an example of a basis transformation that only requires 2 planes, regardless of how many modes you're trying to sort. So if we've got HG modes coming in, that's going to be annoying. All right. So we've got HG modes coming in. They hit a cylindrical lens, and they get transformed into Laguerre Gaussian. So all you need is 1 cylindrical lens to start it, 1 cylindrical lens to stop it. Doesn't matter how many modes there are. It's always just 2. And the reason it works is because of the symmetry of the transformation. For those to go from HG to LG, all they need is a phase shift between their X and Y components, which a cylindrical lens can provide. So basically, because all these different modes aren't trying to do completely independent, crazy transformations relative to one another, they're all trying to basically do the same type of transformation. You don't end up needing a zillion phase plates. You just need 2. And as it turns out, another important basis transformation, Cartesian to Hermite Gaussian, also requires hardly any phase plates. So if we have a grid of points like so, x, y, and we map each x, y position to mn index, we hardly need any phase planes to do that transformation. And then once we're in the Hg basis, we can easily convert to the Lg basis using two cylindrical lenses. Like so. So here we've got our grid of spots, propagate through first plane, second plane, third plane, and then map one position on the one side to a particular Hermite Gaussian mode on the other side. Like so, like I had before, modes go in, bounce, 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 bounce. There's a phase masks there, mirror, and then the sorted spots on the other side. And that's just what some of the details of how it actually, the dimensions are. So we implement the phase mask on something called a spatial light modulator. So a spatial light modulator, if you haven't used one before, is just like a little liquid crystal display. Basically, it's got little liquid crystal pixels on it, and then you can program different values of grayscale to equal different amounts of phase. On the computer, it just shows up like another computer monitor, basically. All right, but how do you know what to actually put on the phase plates to do the desired transformation? Well, for that, we use an algorithm called Wavefront Matching, sometimes also called adjoint optimization. And the name of the game here is we've got modes coming in from the left, we've got modes coming in from the right, and we want to make them the same. And we're going to make them the same by using these phase planes here along the way. That's the only thing we do have to play with. So we've got modes coming in, modes coming out, propagating both to the same plane, forward, backwards. And then we get each pair of input and output modes, overlap them, and then sum those overlaps together, and then take the phase, and that becomes that first phase mask. So what we did there was kind of basically put the average phase error between the forward and backward modes as this first mask. Okay? Trying to match them as best we can. Propagate to the next plane, we do exactly the same thing. Each pair of input and output modes that we're trying to match, spatial overlap, sum all the overlaps together, take the phase, that's the next phase plane. And then we just keep doing that. Plane to plane, back and forward, back and forward, back and forward, back and forward, keep trying to match the phases, match the phases, match the phases, and then hopefully the amplitudes will follow, and they do, usually. And then after one pass, in this case, we can see that the forward and backward fields have become quite similar already, even after just one pass back and forward. And you might think this algorithm seems kind of, well, at least when you first do it, you think this is kind of a naive algorithm that's not going to work. But it actually works pretty well, even based on even how simple it is. There's lots of little tweaks and stuff you do to make it work very well, but the gist of it is pretty straightforward, actually. Here's a calculated mask set. So we've got 7 masks. We're going to be using that to sort 210 spatial modes. So Cartesian side over here, Hermite Gaussian side over here. We've got the phase. We've got the shade, just telling you roughly where the field actually is on this mask. So that's what the actual raw mask itself looks like. And that's what the intensity looks like. That's the next level crash now. All right, that thing's full on restarted. So most of those slides were video. Those last 2 were static frames, and that's what killed it. All right, this is saying something in Spanish. Something normalmente probably means normal startup. I'm guessing. All right. I mean, I could also plug in my laptop, maybe. Maybe I'll do a race. We'll see which one starts first. Am I going to have to log in or anything for this? through of the device and just see how each one of those 210 modes evolves through the system. Here we've got all 210 modes. We've got the fundamental mode at the top. We've got the highest order modes at the bottom. And here we've got the sum of the intensities of all of them. Starting off on the XY grid side, propagate through, first plane, second plane, third plane, fourth plane, fifth plane, sixth plane, and seventh plane. And now we've got Hermite Gaussian modes. Well, obviously, these all exist in the same place, right? They're just in a grid so you can kind of see what's going on, although you probably don't have much chance of seeing that at the back of the room. Now, how did it do that? That's a good question. So it's calculated numerically. It's not defined analytically. And again, it's designed by a machine. There's no guarantee that you'll be able to understand the solution that it gives. Case in point, here's something which has been designed by a similar sort of process where this thing here splits wavelengths 1300 and 1500 out these two ports. But looking at it, you don't really have any sort of intuitive understanding of exactly how it did that, right? No matter how long you stare at it, you're probably not going to guess that that's how it works. Okay. But we're actually not as bad as that. This one, you can actually get some intuition for how it does what it's doing. Now, as it turns out, when we're doing the Fourier decomposition, we needed to use parabolic phase, so para 2. And what the parabolic phase does is it maps xy position to xy tilt. It turns out that for this transformation, we need cubic phase, the power of 3. And what that does is it maps xy position to xy focus. And it also makes airy beams. Now, if you look here when it gets to the center, you get this structure here, airy beam, that looks quite a bit like at least a quadrant worth of Hermite Gaussian mode. And what it's kind of doing is splitting the beam up into these airy beam-like quadrants and then kind of collapsing them all together to approximate Hermite Gaussian modes. So if we watch it again, somewhere around here, you've got this sort of airy beam-like quadrant here, side lobes, and then it keeps collapsing these side lobes in together, 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 and then collapses them into the main beam to form the other dominant lobes that a Hermite Gaussian has that an airy beam doesn't. Or if we zoom in closer, you're not going to be able to see it, but if we look at one of these, for instance, this little airy beam here, and then these little side lobes coming in from the side about now that collapse into the main beam, and we've got our Hermite Gaussian mode. So that's the very hand-wavy version of how it does that. I'll skip over that for time, but basically you can get pretty much a good chunk of the way to this transformation using just tilt, focus, and cubic phase. So these three masks here, that's all they are, and it does most of the work for you just on that. And most of the rest of the planes you end up devoting to trying to clean up these side lobes which shouldn't be there. Here's another extreme case where I just gave it lots of planes, 101 planes instead of the normal 7. And here I'm just trying to see what type of transformation does it do with basically no rules, where it can just do whatever it wants, do whatever kind of transformation it pleases, and just see what kind of features that has. And it's got the same basic features. So we go through the transition. Here, makes that sort of airy beam-like quadrant, side ones, collapse, 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 and then into the main beam. And because we've got so many planes now, and because these are also very, very closely spaced together, the transition is basically perfect, and you could also see that there's hardly any phase used in any one plane. It's very smooth transition, again, like a photonic lantern. If we look at just one mode, one of the higher order modes, makes a bunch of lobes, and then you can see it, again, split up into sections, and then collapsing sections together, working on them independently, and then sticking them into the main beam. Very hand-wavy explanation. Okay, now, all of that so far has been the simulation and design of the device. What about the actual measurement of how this device performs in practice? Characterizing a 210-mode device is a task unto itself, but we've done it like so. We've got our multiplane light conversion system, and on the input side, we're feeding in spots of light one at a time, and then we're measuring what comes out the other end on a CCD camera and performing off-axis digital holography. To explain that in more detail now, we've got our swept laser, because we're measuring it as a function of wavelength. One signal arm goes in here, bounces around, comes out the other side on the camera, and then the reference arm gets interfered as like this quasi-plane wave at an angle with our beam that we're actually looking to measure. And with that, we can reconstruct the full spatial field, a bit like Peter was talking about yesterday when you're reconstructing the field in the time domain with coherent detection. So this is real data. That's what you actually see in the lab. We've got our raw CCD camera image. You Fourier transform it, and you get something like this. It's got 3 terms. It's got a DC term, which is full of junk that we don't care about, and it's got the 2 reconstructed fields, conjugates of each other on either side. So we just pick one of those, set everything else to 0, Fourier transform it back, remove some tilt, and you've got a reconstructed phase, amplitude and phase from the CCD image. And then you can overlap with each of the modes to work out what the actual modal decomposition of that field is. Here's the measured results for all 210 modes at the center wavelength. Goes through quite fast, so you have to trust me that they all have the right number of rings and the right helical phase fronts. So we've got 20 groups there, 210 modes. If you don't put the cylindrical lenses at the output, you can see what the Hermite Gaussians look like raw coming out of the device. Again, right number of lobes, right phase relationship between the lobes. They're all red or blue, indicating 0 or pi phase. That's what the coupling matrix looks like for the simulated device. So spots mapping to modes. Ideally, that would be an identity matrix, and it's pretty close. I've got this on logarithmic scale, so you can actually see stuff. And then we measure this. So ideally, one spot would map to one mode, but you do get some extra additional crosstalk. Again, keep in mind it's log scale. The main problem we run into on the spatial light modulator is that the pixels tend to crosstalk to one another. Ideally, you would program one pixel to be one thing, the next pixel to be something completely different, and they wouldn't have any crosstalk at all. But in practice, the liquid crystals are kind of viscous, and also the fields fringe between the pixels, so they do crosstalk a little bit. So if we have something like this on our SLM, and we're trying to wrap from minus pi to plus pi, black to white, ideally it would transition instantaneously in green, but in practice it changes more on the scale of like half a pixel. And that causes just some extra scatter. This is what the actual SLM, when you're programming an SLM, that's what you actually see. Right, so that's the phase masks. Black, 0 pi, white, 2 pi, and there's our 7 masks, like so. We tried to move the phase wraps around to positions where there's not much light as much as possible to avoid that problem. Because we thought we'd get greedy, we also made a 325 mode device. Again, you can see very quickly that it's got the right number of helical phase and number of rings. It is starting to push it a bit when you get to 325, but it still works. Again, remember, if we had been in the worst case here and needed a full 2n number of phase plates, this would require 650 phase planes to do that transformation, but instead we've used 7, which is a bit more convenient. And there's the coupling matrix for the same thing. It's slightly worse performance than the other one, but it's also got 50% more modes. All right, I'll wrap it up there. So like I said, most of these talks are on the YouTube. Also, shameless plug, I've got positions open as well. So there you go. Thanks, guys.
Thank you very much, Joel, for your very interesting talk with a lot of image. I know previously that your talk was going to be very visual. I'm sorry for the computer. But sometimes
too visual.
Yeah, sometimes computer fail. Okay. So now it's time for questions. First one, please.
Sorry, but I didn't understand how do you calculate the phase mass?
Yep. So what you do is, like I said, you've got modes coming this way, modes coming that way. And if you want the transition to be lossless, then those fields going forward and backwards have to be the same everywhere. Okay, have to be the same this way, have to be the same that way. So you're trying to match the phase of the modes going that way and the modes of that going that way to make them the same. So you just put whatever you need to do that on the phase masks. And then the amplitude tends to follow as well, and then they just become the same field forward and backwards.
Just move the liquid crystal and you have the phase match? Or?
Oh yeah, so that's when you're calculating it, and then when you want to display it, so you use the spatial light modulator, and it's like this big. It's like an inch sort of big, little 8 micron pixels on it, and you literally just write pixels to the monitor. The computer thinks it's another monitor, and you just write pixels to it, and then it displays that phase.
Are you using a special spatial light modulation, or is it a normal one?
It's a normal one. It's just HD resolution. It's not particularly fancy. It's a pretty standard.
Is it working properly in the third window?
It's working properly?
In the third window, in the communication window.
This is work in C-band.
Yeah.
Yeah, we designed this one for C-band. But also with this device, there's simple scaling rules, and you can just translate the exact design to a different wavelength. Just by making things bigger or further away, it turns out to be exactly the same.
Thank you very much. Professor Yablonami, please.
So I was very pleased that you mentioned adjoint optimization during your presentation. And of course, it's great for the things that you've described, transforming one image into a different image, and so forth. There is a similar industrial problem that existed a few years ago, and that is how to design a phase mask, or not a phase mask, but even an amplitude mask that would project out the right image so that we can use photography to print integrated circuits.
Okay.
And once again, you go through adjoint optimization. It's very similar. You have a mask, but you want to get a completely different image further down. You want the image to resemble the transistors and so forth.
Like a Gertzberg-Saxton type thing in that case?
They don't. Well, there are iterations in that case as well.
Yeah.
But I didn't quite see that it was exactly the same as what you're describing.
Yeah.
But the power of this adjoint optimization is something that is not normally taught in physics.
Yeah.
And but it's of great importance in engineering. And so in effect, you're engineering a transformer that transforms modes, many things. It turns out that the mechanical engineers were using this before.
Yeah, when you Google it, that's what comes up. Yeah.
And so us people in electromagnetics were kind of late to jump on this. Yeah. And in other fields, they were using this, for example, to if they wanted a very stiff mechanical object with the least possible weight, and to get the shape right. And so many applications in many fields of science.
Cool.
Thank you, Professor Yablonami. Other questions?
Which you think is the best way to launch a specific mode in a multimode fiber?
It's good. Okay, I guess why are you doing it? I guess is one question. So I normally do it. I didn't even talk about that. Ooh, did I have a slide on that? Maybe I did. I may have. There we go. Whoop, whoop. Sorry. There, is that it? So that's how I normally launch a mode into the fiber, is using one plane of a spatial light modulator. So I'll use a laser pointer. We got the single mode fiber comes in here, Gaussian beam, some polarization optics inside, that bounces off the SLM at the bottom, then gets recombined and then gets focused into the multimode fiber. So I put whatever phase mask I want on there to convert the Gaussian to a higher order mode. That's how I often do it. The downside of that one is that it's got mode dependent loss. It's some easier than others. The multiplane light conversion system doesn't have that. So if you use two planes, you don't have the loss.
And it's suitable for this application also, the multiplane system?
Yeah, so that device that I just presented, that can easily launch not just one mode, it can launch all the modes simultaneously. Okay. So it's like a big mode multiplexer.
And also one mode each can...
Yeah, so basically if at the input, depending on where you put the beam, it will launch that mode into the fiber.
Thank you.
Any other question? Okay, in this case, let us to thanks again, Professor. Before to close the session of this morning, 2 comments. One comment is that in the closing ceremony, we are going to deliver the diploma of the people that are in the room that you can use for PhD merits in order to take into account. But as everyone knows, the attendee is very exactly controlled. So if some number of people it doesn't be in the room, I'm talking about a PhD student mainly. In this case, they are not going to able to get the diploma. Okay, they are just only one receive in order that you be here, but not the official diploma. Okay. This is the first comment. The second comment is that now we have time in order to get lunch, everything you like to do, and then we are going to meet again at 3:30 p.m. 3:30 p.m. in order to develop the round table on communication challenges. Okay, so up to a few times. Thank you very much.